look first of all for this magnetic vector potential, which we have introduced, that this magnetic vector potential is not unique. So in this sense, when we add any scalar potential as shown here, which is the gradient of psi, then clearly if you compute the curl of this new vector potential, then we know that the curl of the gradient of a scalar potential is equal to 0. So we get here the curl of A prime, and that shows us that we can add any arbitrary gradient functions to our vector potential, and we get the same magnetic flux density B. So the vector potential itself is not unique. Well, if we are just interested in B, then it is a not so big job. However, if we also want to have a unique magnetic vector potential, then it makes sense to use, for example, the Coulomb gauge. The Coulomb gauge then is the following, that we set the divergence of the vector potential to 0, and that means we have to solve an additional equation. So if we go back to our partial differential equation, then as you see here, then we also have to solve, in addition to this partial differential equation, this second partial differential equation, that the divergence of A is equal to 0. Now, if you have a look for the 2D case, so we are computing the magnetic field, let's say, on a cross section. It is very often done for electric drives. Then the magnetic vector potential has just a z component, and the coefficient A of this magnetic vector potential is dependent on the x and y coordinate. And now it is clear, if you compute the divergence of such a vector potential, since we have just a z component, and the derivative of this A as a function of x and y with respect to z is 0, this is automatically fulfilled. And the same holds true for the axisymmetric case. In the axisymmetric case, we just have one component of the magnetic vector potential being different from 0, and this component is the phi component. And so in this sense, A is a function of r and z, and the direction is exactly going in circumferential direction. So for this case, also the divergence of the magnetic vector potential is 0. So this is automatically fulfilled. That is the good story, that in 2D we have a automatic gauging, because the magnetic vector potential, the divergence of it, is automatically 0. However, this is not the case in 3D. Okay, so if we now go on and do some investigations in the modeling, especially in 3D, you know that especially coils with a high filling factor have a lot of turns, and it is very difficult to really model all these details geometrically. You can do it clearly. However, the discretization, meaning the mesh generation, will be a real big challenge. However, if you have a high filling factor, meaning that you have a lot of turns around, for example, this ferric core, which makes up your coil, then it is enough when you substitute the complex winding structure by a hollow cylinder, and that is then quite easy to be modeled geometrically, and also when you do and perform the meshing. In this case, the current density, as it is, for example, a known quantity and being on the right-hand side of our partial differential equation, then it will be also simplified, that you not take into account the correct direction of the current in the winding, but you take it as a hollow cylinder, and then the current density will have, as shown here, just a unit vector in circumferential direction. Yeah, and as we know, the current density is the current over the cross section of one winding, yeah, that is of one winding, and that we can simplify to compute with the cross section of the conductor divided by the number of turns. NC is the number of turns, and in order to also take into account that you have a filling factor being smaller than 1, for most of the coils you will have filling factors 0.9 to 0.95. You also take this into account with kappa when you know it in this case. Okay, so you see in this sense, especially for 3D modeling, this will reduce quite heavily your burden you have to do within the pre-processing in order to set up the geometry as well as the mesh. Now concerning the material behavior, as you know, concerning the ferromagnetic materials, we have diamagnetic materials, paramagnetic materials, and ferromagnetic materials. And as shown here, in this case, diamagnetic materials more or less have a magnetic permeability being smaller than relative magnetic permeability being smaller than 1, which means the magnetic field will try to go more or less around this material. For the paramagnetic case, you have a small relative permeability larger than 1, so you already have some concentration, but the materials for which we are using in order to guide the magnetic field will be ferromagnetic materials, and here you see the strong concentration you have there within such a material. Now, when you try to measure the behavior between the magnetic field intensity H and the magnetic flux density B, you will find out that you have even such a hysteretic behavior. So starting, let's say, at the demagnetized state, you when you measure B and H, you will go along the so-called Virgin curve, the first magnetization curve as shown here. And when you then reduce the magnetic field intensity, you will see you go back on a different curve, and even if this H is equal to 0, you have a remnant magnetic induction called as here BR, and you need a magnetic field intensity in opposite direction for some value in order to make B equals 0. At the end, you see that you have such a hysteretic behavior, and for a lot of materials, we have here the width of the hysteresis quite small, which means we will use an equivalent nonlinear curve and do not take into account the hysteresis. The hysteresis itself is a quite difficult topic to be modeled because we have a vector field, so you also will need any vectorial hysteresis operator in this sense. Okay, so we differ concerning ferromagnetic materials between the magnetic so-called soft materials, where these two values BR and HC, the correlative magnetic field intensity you need in order to make the remnant magnetic flux density in the material to 0, are quite small, and these are, for example, iron or steel, and they have hysteresis curves with a small width, and we will substitute the hysteresis curve more or less by a nonlinear curve. On the other hand, what we also need to consider are hard magnetic materials. These are the so-called permanent magnets, and for those, clearly you want to have a large remnant magnetic flux density and a large magnetic field density, corrosive field intensity, in order that you really can store a lot of energy in such a permanent magnet, which then you also use for exciting your system. And that is here the curve. So you once have to magnetize this material, and as you can see, when you switch off the external magnetic field with which you have magnetized the material, you end up here at BR, a remanent magnetic flux density, and that should be quite high. You see here on the left, you see here some values of some different materials used in practice, and as you can see here, this is one of the best materials currently we have, which is a neodyne material with iron and bore, and you see you have a remanent magnetic flux density of about 1.15 Tesla, which is quite large, and you also have a large corrosive magnetic field intensity Hc, so the product, which is proportional to the energy, is also quite large. And when you use such a permanent magnet within a magnetic circuit, then actually this is more or less the working area where this permanent magnet is working, and according to the load, which you can show here by any straight line, you then, for example, get such a working point. What is interesting for such permanent magnets is that they have more or less almost a straight line, so it is somehow a linear behavior in this working area, the second quadrant, between H and P, and for most cases you will also use here a linear material law in order to include permanent magnets within your computational partial differential equation. Okay, the second material parameter we have within our partial differential equation is the conductivity. For the conductivity, you see here different values for typical materials used like iron or copper, for example, which we are using in order to guide the current in the coil structures, or for a steel here. So you see that you have a quite high conductivity for those materials, which is up to 10 to the power of 7. The main dependency is more or less the temperature. I have here now written it down, as we mostly do it in electrical engineering, not for the conductivity, but for the specific resistance, which is just 1 over the conductivity. And so you see the thermal relation for this conductivity can be written in this form when you know these two parameters, which are fitting parameters due to measurements, the alpha, which is also called the linear temperature coefficient, and beta, which is the quadratic temperature coefficient. And you see here, for example, for steel, between 0 Celsius degree and about 1000 Celsius degree, how this conductivity with increasing temperature decreases. So especially in a coupled field problem where you, for example, heat up any electric conductive materials, for example, by eddy currents, which will be the second topic of this course, then you should take into account that this conductivity is a function of the temperature. Yeah, and what is also a very important part within the modeling and numerical simulation of electromagnetic fields is to know about the interface conditions, sometimes also called transition conditions, which means how does the magnetic field behaves when it comes from a material with material parameters being different in a subdomain 1 and 2. Yeah, so as we can see here, we have here B1, and let's say B1 could be, for example, iron, and P2 is another ferromagnetic material, and they have different magnetic permeabilities or relativities. And the question is, how does the normal and tangential component behaves? And the main equation from Maxwell's equation we take out in order to get this behavior is the equation Maxwell has added to the system of equation, and this is that the divergence of B is equal to 0. Integrating over the computational domain and then applying the integral theorem of Gauss, or also called divergence theorem, we see that the closed surface integral, which could be the closed surface integral of this box here, is equal to 0. Yeah, and now we just cut out such a small box with a height equal to b, and we let go b to 0, which means evaluating it, and when here this box has a very, very small dimension, then we can more or less say that the b is constant, and the evaluation means in this sense then that we just have here the following. We already have divided here by the cross section or surface gamma 1, and so we see that the normal components have to be equal to 0, which means that the normal component of the magnetic flux density is continuous. However, according to our constitutive law between B and H, we clearly see that when we have here two different materials, that the normal component of H immediately at the interface jumps according to the ratio of the permeabilities. Now, we are also interested about the tangential component of B or tangential component of H. For this, we here use the Maxwell's equation in integral form according to the first Maxwell's equation, so which is coming up from Ampere's law. And as we have set it here to 0, it means we do not assume that along the interface we have here any current, surface current density. Okay, we now can transform this cross-sectional integral to a contour integral, a closed contour integral over such a closed contour. Yeah, and since this has to be 0 and we let go here the distance to 0, which makes sense because we want to end up at immediately the interface, well, then it is nothing else in this case that when this box is very small and we go towards the interface, we can say that the H1 and H2 components are constant. We take the dot product with S. S is in tangential direction concerning the interface. Yeah, and in this sense, we clearly see that we have a continuity of the tangential component of the magnetic field intensity. And on the other hand, using our constitutive equation between B and H, we get that the tangential component is jumping. So in this sense, we already see that the magnetic field is a quite complex physical field, so you will not have really smooth solutions in this sense, because you will have interfaces, especially between iron, for example, and air, where you more or less have jumping physical quantities concerning B and H. So this needs special care when we will then turn over the partial differential equation to the weak form and perform a discretization with finite elements. For this, we are now considering such a computational domain with two subdomains. Yeah? So we assume that we have here a subdomain 1, and we have here a subdomain 2. And as you see, we also assume that we have here a permeability mu1 and the conductivity gamma 1, and here we have a permeability mu2 and the conductivity gamma2, and along these interfaces the material parameters are jumping. So we have an interface and we have our outer boundary, and within this domain we want to compute the electromagnetic field in the quasi-static case. And for this I take this partial differential equation. For the time we neglect any current densities due to moving deforming bodies that we will take into account later. So what we have is here the time derivative, the partial time derivative of the magnetic vector potential scaled with the conductivity. We know these are eddy currents or models eddy currents induced in electroconductive bodies. We have our so-called curl operator, where I use now the relativity, and we know that the relativity more or less is a function of space, as we see here. It could be constant within a subdomain, but has a total different value within another subdomain. And especially for ferromagnetic materials, it will be a non-linear function depending on the curl of the magnetic vector potential, so depending on B, our magnetic flux density. Okay, furthermore, we clearly need boundary condition, and for the first case, we use the simple boundary conditions which are always fulfilled. As we know, the magnetic field is a so-called solenoidal field, and for solenoidal field you always have closed flux lines, which means the flux lines cannot go out of our domain. So they cannot go out of our domain, and that means, so I just put here, this is for example the normal vector, and so the normal component along the boundary of B should be 0. And this is equivalent as taking the cross product between the magnetic vector potential and the normal vector, which means what we will get out here is just the tangential components of the magnetic vector potential along the surface, and they should be equal to 0. So this is the transformation between in 3D if you have such a field between a dot product and the cross product, when you have the relation clearly between B and H over the curl. Yeah, and in addition, we should not forget we have quite a lot of interface conditions. We have that the normal component of B should be continuous, so B1 in normal vector minus B2 in normal vector should be 0. The minus is coming in this sense because I perhaps can also put it here in with another. So if you look here at subdomain omega 1, then along this common interface, this will be the normal vector because it's always pointing out, and we call this, let's say, the normal vector n. Yeah? And now I take really another color. I hope I have another color. And if I look now for subdomain omega 2, the normal vector clearly, since it points out of the domain, will be minus n. Yeah? And that is why we get this minus in as shown. Then we have the tangential component. In order to get the tangential component on a surface, you take the cross product with the normal vector should be continuous. And don't forget the divergence of our current density has to be 0. And that also means that the normal component of any current densities you have there should be 0. Which means at the end, if we now substitute here this with the magnetic vector potential, then we have here clearly the same as on the outer boundary. The tangential component should be equal, should be continuous along the interface. For the tangential component of H, you get here this long expression where we also have to take into account that we have here our material parameter. Yeah, and this is also a very interesting part in this sense, we could have here a conductive body, for example, iron or aluminium or whatever, and on the other hand, it could be air, for example. In air, the conductivity is 0. In aluminium, the conductivity is quite high, so you even have here a jump from a high value, for example, to 0. So we also have to look that such an interface condition is fulfilled, not only in the continuous setting we have, which means our weak formulation, but then also when we perform a discretization by finite elements. Okay, so this is our setting, and just some preliminary things. In 2D, everything is okay. We can use the standard finite elements, sometimes also called nodal finite elements, because the unknown, in our case the vector potential, is at the finite element nodes, and we use this standard approximation basis functions there. On the other hand, if you do this in the 3D case, then you really run into trouble, and you will see that you get at least locally wrong results. Yeah? And that is very important to realize. And as an illustration, I will show you what can happen in this sense. If you look at such a domain where we have two different ferromagnetic materials, and in this domain, for example, in this red domain, the relativity is going to 0, which means you have a very high permeability. Since this relativity scales our curl-curl operator, it would mean in the limit going to 0 that this domain can be excluded. However, if you then look at the remaining domain, then it is clear that such a domain clearly is non-convex, because if I take any point here and connect it to any point on this side, I go here out of the computational domain, since we have excluded here the red box due to the fact that the relativity is going to 0. And for such problems, you get absolutely wrong results if you have such non-convex domains, and you need some special operation, so-called a decomposition of the vector potential, which is getting quite complex because you have to find all these kind of re-entered corners, as you have, for example, here. So there are some formulations, but in no commercial programs, just in some research programs, and it's getting very complicated, especially for the implementation. In this case, the correct discretization is done with so-called Nedelec or edge finite elements. Nedelec was the scientist in 1980 who was the first who really found correct basis functions, and since the magnetic vector potential is a vector, and especially the magnetic vector potential should have a continuity of the tangential components, he introduced these so-called edge finite elements. Now, edge finite elements are in this sense really different, because as you can see here, the unknowns are along the edges. Yeah? You know standard finite elements where the unknowns are here at the nodes. But now the unknowns are along the edges, and the unknown vector potential is at the end a scalar unknown, because you project it in the direction of each of these edges, for example, of a tetrahedron, or if you have a hexahedron, or what element you ever use. And what makes it also different to the standard nodal finite elements is that, as you can see here, that the basis functions are now vector functions. Yeah? That is quite different to the standard elements, where the basis functions are scalar functions. Even, for example, if we consider elasticity, so the mechanical field, we have used for each degree of freedom in x, y, and z for the mechanical displacement the same nodal scalar basis function. Here it is different. The basis function itself is a vector, and the unknowns are scalars where we project the magnetic vector potential in the direction of the according edge. However, you have a full machinery how you compute such vector basis functions, and the nice thing is you can show that, for example, you can use the Lagrange nodal shape function or basis function in this sense that I and j are the two nodes. For example, as shown here, it could be the node 1 and the node 2. And to get the basis function now along this edge, you take here ni, for example, n1 gradient n2 minus n2 gradient n1. I and j are now just the levels of the nodes as shown here, 1, 2, 3, and 4. Yeah, so you can use the standard Lagrangian shape functions, but with these Lagrangian shape functions, you construct now a vectorial basis function which you are using within the so-called Nedelec or edge finite element method. So that makes the things quite different, but what is now clear is the following. Since these basis functions and the unknowns are really the projections along the edges, when you have two elements and the two elements have different materials, then by definition the continuity of the tangential component of the magnetic vector potential is fulfilled. Yeah, that is by definition, which we do not have for nodal finite elements. And on the other hand, which is important, the normal component of the magnetic vector potential can jump along such an interface. And as we know from the transmission conditions, this normal component should be able to jump, which is not possible with nodal finite elements because you fix normal and tangential component. Here you just fix with this ansatz the tangential component of such a magnetic vector potential. Okay, so we know now how to discretize it, but before we discretize, you know, our machinery is to first introduce a test function, multiply the test function with the partial differential equation. In this case, it is a dot product because we have a vectorial unknown, so also our test function will be a vector, we call it A prime. We integrate over the whole computational domain, and this has to be 0. Now on this second term, we can apply an integration by parts, and the surface integral in our case is then 0 because we have the standard boundary condition that normal vector cross product with the vector potential is equal to 0, so that we guarantee that on the outer boundary the magnetic flux lines are parallel to the surface and we have no flux lines going out of the computational domain. And for these cases, the surface integral is 0 and it remains just our volume integral, and very similar as for a standard Laplacian operator as we have discussed in the other topics, we have now the curl of the test function, so a first order partial derivative dot product with the curl of our unknown vector potential, which is also a first order partial derivative with respect to space. Okay, so this is our weak formulation now, and as discussed just before, our approximation is now again as we would do it with our standard finite elements. However, we use the edge basis functions, and the edge basis functions as shown here. Okay, and the unknowns A, B, the sum goes B equal 1 to the number of edges now, not over the number of nodes, number of edges, because the unknowns are along the edges. And these unknowns are the projection of the magnetic vector potential along the edge. So we take A dot product ds. Okay, so substituting this space discretization with such ansatz functions into our weak formulation, we come up to the matrix system where we now have the following system of ordinary differential equations in time. So A dot means the partial derivative of the unknowns we now have along all the edges in our computational domain with respect to time. And we will have such a system where we call this here a so-called mass matrix, which we call here, okay, I just want to get the pencil. So this is our mass matrix, which we will get out from the first term here, which we will see in a short time, and the second term, as it is called the stiffness matrix for electromagnetics, which we will get out of this term here, is equal to a right-hand side, and the right-hand side is due to some given current. Sorry, I didn't want to have this one, I wanted to have another color. So we have here this F, and that is coming out from this part of the weak formulation after we substitute our approximation. Okay, so in this sense, just explicitly, so all the entries of our mass matrix are now as shown here. They are computed accordingly by this relation here. Since we put in our basis function, we have the dot product between these vectorial basis functions AP and AQ for the HP and for the HQ, and the dimension here is the number of edges we have within our finite element. For example, for a tetrahedron, we have 6 edges, so it is a 6 by 6 matrix. Yeah, then we have the stiffness matrix, which is a little bit more complicated, and where I have written it here in an abstract way, but we will explicitly look how we can compute these curl B operators. And the last one is then our right-hand side, which is computed according to this relation. Okay, so I think this mass matrix entries are standard, and the entries for the right-hand side are standard when our current density is given. However, this part here for the stiffness matrix, we should investigate more. And for this, we first of all just compute for any edge P within a finite element here explicitly written as the nodal basis functions. We have to compute now the gradients of it, and as you know, we clearly will get out here a vector. And and the vector is shown as here. We have ni partial derivative of j with respect to x minus nj partial derivative of ni with respect to x, the x component of our vectorial basis function. This will be the y component, so the derivative of y, and then the z component just explicitly written down here by after computing the gradients. Okay, so this is what we just have computed, and what we actually need is our curl of these vectorial basis functions, and this is now explicitly computed. We have here our EP, and when we take the curl, then what you get out is this part here, and we now put in clearly the x, y, and z components, so the x, y, and z component of the vectorial basis function, which is here called Ez for the z component, Ey for the y component, and Ex for the x component. And since we use now, in our case, these linear functions, any mixed derivative or second derivative will be 0, which means what we get out is then this explicit expression here. And with the explicit expression here, we have now computed our curl of such a vectorial basis function. So these are the standard Nedelec elements, as I have shown here, which compute the basis functions out of the nodal basis functions by the equation I have shown you. And then when you apply the curl of such a vectorial basis function, it is just the curl as you are used to compute for a vector. Okay, so in this sense, we know now how to set up our discrete system. Still, we should not forget we are still continuous in time, so we'll also have a discussion about the time discretization. Up to now, I first want to go to the boundary condition, because I would say for electromagnetics, it is not as straightforward as, for example, for a mechanical field. You should already know a little bit how the magnetic field looks like when you explore any symmetries. Yeah? If you don't explore any symmetries, then you always have this as a standard. At the outer boundary, it is not allowed that any flux lines go out of the domain, because we have a solenoidal field, we have closed flux lines, which means that the dot product between B and N is equal to 0, or transforming it to the magnetic vector potential, since B is equal to the curl of A, it means that the cross product between A and the normal vector of the surface has to be 0, which means that the tangential components of the magnetic vector potential has to be 0. This is now simple because we use these edge finite elements, and all these edge unknowns on the surfaces are exactly in the tangential plane concerning your surface, which means in this case, in order to force that B dot n is equal to 0, we just take all these edges on the surfaces and set the according unknowns there to 0, and we automatically then get the physical condition that we get closed field lines. Clearly, what we have to take into account, in magnetics we also have stray fields, so we also have fields within the air, and there clearly you should not limit your computational domain too strongly, otherwise you compress your physical magnetic field, and the numerical computation will have a large error. So you always have to make your computational domain as large, so that you also include the main parts of the stray field in air, and don't compress, in this case numerically, more or less your physical field. Okay, let's have here an example. In this case, let's say we express B by the three components, x, y, and z component, and we have a normal vector on the surface, which, for example, has just a z component. So it is a surface which is parallel to the xy plane, and on this surface we want to have that the normal component of B is forced to be 0. And as you know, we have to apply it correctly to the magnetic vector potential. Now, the tangential component for such a surface is something like 1, 1, and in order to scale it to a length to 1, it's 1 over the square root of 2. It's clear? So this is then the tangential plane, so it is really the tangential vectors on this surface. Now what we have to force is that B in n is equal to 0, and that means that since the normal vector has 0, 0, 1, it means that we should have a p vector which has just the x and y component, and the z component is equal to 0. And that then also will guarantee that you have magnetic flux lines along such a surface, and they are not going out of the volume. Okay, now what we have to fulfill on the other hand is that the tangential components, so instead of A cross n equals 0, I can also write its equivalent. I can also write it equivalent in this sense as A dot product with the tangential vector equals 0. Yeah? And doing this, as you know, we will get out the following. Since the tangential vector has a 0 in the z component, and we should have then a magnetic vector potential just having a z component, or allowing a z component different from 0, and automatically the x and y component, so the components in the tangential plane, should be 0. Okay, so if we do this, then we get the following. If we take of the curl of such a vector potential, just having the z component different from 0, we get automatically, as you can see here, magnetic field which has just values, or can just have values different from 0 in the x and y component, and these are the components living in the tangential plane. Okay, so in this sense, you see what we have to force, and the nice thing for the edge finite element is that on such a surface, which is the outer surface of your computational domain, we always set all our edge degrees of freedom to 0 for the magnetic vector potential. So the magnetic vector potential just can have a component in normal direction, and forces that we fulfill B dot n equal to 0. Okay. Now, if we have any symmetry, we want also to explore symmetries. Clearly, you know, in 3D, perhaps due to special discretizations in order to resolve eddy currents, whatever you resolve there, you end up in huge number of unknowns, and therefore if you have some symmetries, but not only a geometric symmetry, there should be also the symmetry in the magnetic field, then you should explore it. And along a symmetry plane or surface, it can be also the case that the normal component of the magnetic flux density is equal to 0. Okay, so in this case, we already know what we have to do for the magnetic vector potential. However, you could also have surfaces where the tangential component of the magnetic flux density is equal due to symmetry condition. And in this case, you should do nothing, because then you have everything, because your magnetic vector potential lives on this surface. It has no normal component, and will then automatically fulfill this boundary condition that the tangential component of B is equal to 0. Okay, so that is the nice thing. When you have such a symmetry, then you do nothing and don't set any degrees of freedom for the magnetic vector potential to 0. And that I want to demonstrate by a simple example as shown here. We just have here a straight conductor, and we have here an iron core going around this conductor. Well, you could here explore a lot of different symmetries. Let's say you want to compute it just with a quarter symmetry. Well, then we have the following boundaries. We have here on the top to specify the correct boundary condition and on the bottom. And then we have this side. You don't see it, sorry. So we have here the top, the bottom as a surface where we have to define the correct boundary condition. We have here the surface where x is equal 0, here the surface where y is equal to 0, and then we have the surface in circumferential direction, so the outer boundary. Now at the top and the bottom, well, it is an outer boundary, and clearly we have to fulfill our standard boundary condition, which means we set all our edge degrees of freedom at these surfaces equal to 0 according to this relation here. Now we have the plane x, the plane x equal 0 and y equals 0, which means this front plane and this front plane. So shown here, this front plane and this front plane. And here we know that the tangential component of the magnetic flux density should be 0. That always the magnetic field goes around a current conducting conductor, in this sense, as we know from Ampere's law. So that means that we have exactly at these planes just a normal component of B, and the tangential component of B is equal to 0. And that we also have discussed up to here. So for these two surfaces, well, we know that we do nothing concerning the magnetic vector potential. And the last case is the outer boundary, where we have to fulfill that B. One moment. Was too fast. That the outer boundary where the normal component of B has to be equal to 0. So in this sense, we again have our standard boundary condition where we set all degrees of freedoms along all the edges on this surface equal to 0. So you see, the main part is in this sense, you should have already an idea how the magnetic flux lines or the magnetic field looks at symmetry boundary condition. When you know this, you can explore it. If you don't know, then it's better that you don't explore any symmetries and do the computation for the whole setup. And the complex thing is always just that we somehow then know how the magnetic field looks like, if it is just a normal or just a tangential component, and we have to transform it correctly. What we do then with the magnetic vector potential, which is the quantity which we are computing within our partial differential equation. Now, let's have also a look to 2D cases, because whenever it is possible, we clearly will try to compute within a cross section and get in a quite short time compared to 3D simulations a first result, even it is an approximation. Such a setup could be as shown here. So we have such a structure of a conductor, which is very long, as you can see here in this third direction. So this could be one turn of a winding in an electrical drive. And then it perhaps makes sense to really cut along here as shown. And what we will get out here is then such a setup as you can see here. In this cross section, we have in region 1 the one conductor and the of this winding going into the plane, and on the other hand, this conductor is here shown where the current is, for example, going out of the plane. Yeah, so clearly if you do now the computation here for this 2D problem, then on this cross section, then clearly we could just use this outer boundary where we know B dot n is equal to 0, or on the other hand, A dot t is equal to 0. So now let's have also here a look about our relation. We know that in such a 2D plane case, we have just a vector potential component in z direction. So this is orthogonal to the computational domain, which is in the xy plane. And so we have here a vector which has 0x component, 0y component, and we just have a component, z component, where this component depends on x and y. Yeah, when we take the curl of such a vector, which we already have done before, then clearly we get out a magnetic field which is within the computational domain. So as you can see here, we have here the partial derivative of a with respect to y and the partial derivative of a with respect to x as y component, and clearly we have no z component. And that makes sense, so the magnetic field clearly lives within our computational domain. We should be also aware that this is an approximation, especially if you look here at this structure of our turn, then clearly this is a good approximation in the center. However, at the end regions, this is not correct. And one approach, practical approach, is especially for electrical drives, that you really compute just a cross-section, and these end-winding effects you model by some additional electric circuit equations, which you couple to your finite element systems equations. Okay, now if we want to explore symmetry, I just have rewritten here the relation we have, how the magnetic vector potential A looks like, and the magnetic flux density computed by the curl of A. And now what we can see here is the following. I have explored a symmetry according to such a quarter here. So I just have here just half of the conductor where the current was going out of the plane. And so along this line here we have symmetry, and along the y-axis we also have symmetry. So there is nothing to be considered at our outer domain, which is this part here. I wanted to have a different color. So along our outer boundary, we have here no problem. So as we know that B dot n should be 0, or A dot tangential vector should be 0, well, then it is easy. We have here the tangential value is exactly in z direction, so we just set this component, the AZ component of the magnetic vector potential, to 0. So this is more or less a standard in this case, what you do in, what you do here at the outer boundary. But on the other hand, we have here a symmetry and we have here a symmetry. We know that the magnetic flux lines will look something like this, which means along the y-axis you will have no y component of B. If we look here at our explicit expression, that means that the partial derivative of A, the z component of our magnetic vector potential with respect to y, one moment. Sorry, yeah, clearly I have just take here the wrong one. Sorry. What we actually have here is by should be equal to 0, and by equal to 0 is clearly this part here. Yeah? So we see that the partial derivative of the z component of the magnetic vector potential, which we have just named A, should be equal to 0. Along the other boundary, and this is here, we have that the x component of the magnetic flux density has to be 0, which means the partial derivative of A with respect to y should be 0. Yes, and when we combine it, we can in general clearly write it as follows, that the normal derivative of the z component of the magnetic vector potential should be 0, because along the y component the normal vector is the x, is the unit vector in x direction, and along this boundary the normal vector is the unit vector in y direction. So we get here in this sense then a very general expression in 2D, and this relates to a homogeneous Neumann boundary condition, since at the end our partial differential equation for a 2D plane case as well as the 2D axis case are just scalar, is just a scalar partial differential equation, because we have just one unknown as shown here for the magnetic vector potential. Okay, so that would be for 2D case computations. Let's just finish this by also considering an axisymmetric case, a very simple setup of a ferrite core, and the winding structure has been modeled by such a hollow cylinder, where we have given inside the hollow cylinder the current density in circumferential direction as an input value for the right-hand side of our partial differential equation. And as already discussed before, when we were discussing about the gauging, then we know that for the axisymmetric case, we have exactly this relation here, that we have the vector potential has just a phi component, so it's going in circumferential direction, and we have a here, a scalar quantity depending on the r and z coordinate. Okay, so as you know, this will be then the computational domain is shown here. So we have the cross section of this axisymmetric case. Here is the r direction, here is the z direction, and we have here like a rectangular structure, the coil, here the ferrite core, and that should be the outer limiting computational domain. So will be our boundary where we want to compute the magnetic field. Yeah, and as we have discussed, this also holds true now for the axisymmetric case along this boundary we have here. We should have clearly no magnetic flux lines going out, which means the normal component of B should be 0 here. And that's also the case for the rotational axis here. And this is simply fulfilled when you set this phi component of the magnetic vector potential along the boundary to 0, and you get then a correct magnetic field by when you perform your numerical computation. Okay, so this is the 2D axisymmetric case, and before going further to some examples in this sense, and then also looking how to solve especially for nonlinear problems. We take into account the nonlinearity within the ferromagnetic material. We discuss about the time discretization. So the time discretization, as we have seen, after the space discretization, what we have obtained here is now a system of ordinary differential equations, which we exactly have written here. We also have discussed how to compute the entries of the mass matrix and the entries of the stiffness matrix. The point means a time derivative. So the magnetic vector potential depends continuously still on time. And so we will also have to discuss how to do the so-called time discretization. Okay, so for this, similar as for space discretization, we discretize our time interval, in which we want to compute our solution into small intervals from Tn-1 to Tn, as shown here. And this is going from n equal 1 to m when we subdivide it into m time intervals. For simplicity, let's assume we have a constant time step, and this delta t, which is in general nothing else as Tn minus 1. Let's say we have here a subdivision, as you can see here, of the whole computational domain by m subdomains, and then we have a delta t which is equal for each time step. Now, what you apply here is the simpler thing, so we don't do again this introducing of basis functions as we have done for the space discretization. For the time discretization, we apply a finite difference method, and the standard finite difference method is as shown here, that you approximate the time derivative in this sense that you evaluate the magnetic vector potential at time step Tn plus 1 minus the magnetic vector potential at time step Tn divided by the time step delta t. And that is also shortly written that as A index n plus 1 minus A index n over delta t. Okay, so you see this is a simple finite difference scheme in time. You could also do and introduce basis functions, so you more or less treat the time as a further space coordinate, and that would be the method called space time methods. However, the standard approach is that you use finite differences for the time discretization. Now let's go in some details, because what we don't know, how we should take the magnetic vector potential itself. We just have defined now an approximation for the time derivative, but at which time we should evaluate the magnetic vector potential multiplied by our stiffness matrix, and at which time we should evaluate the right hand side. So for this case, the best approach and the general approach is the so-called convex linear combination. So we do a convex linear combination between the two time levels Tn and Tn plus 1 with some weighting parameter. So this was already the standard, that was an approximation. And now for the discretization, we have here of, for example, this term here. We do the following as shown here. We evaluate it at the new time step where we want to compute the magnetic vector potential and scale this with some parameter gamma p, and add to this evaluation of the magnetic vector potential at the previous time step, what we should already have computed, and we scale this with 1 minus the integration parameter gamma B, and that is meant with the convex linear combination. And the same you do for the right hand side. You also do this combination between time step n plus 1 and time step n for the right hand side. Okay, now we can rearrange the terms because we assume that we already know an is here popping up and is here popping up and is here popping up. So we can rearrange it, and what we get out is now this equation here. So that we have as a system matrix the mass matrix plus a scaling of the stiffness matrix scaled by the time step and this integration parameter, and then the unknown vector potential at time step n plus 1. And all the things we know we put to the right hand side. We clearly assume in our part here that we know our right hand side at all time steps we want to compute. And in addition, clearly everything what we know and we had on the left hand side we can put here, because we assume that A, our magnetic vector potential at time step n, is already known. And if it is the first time step, then this an would be the initial condition what we will also have to provide for getting a correct solution in time. So we have different possibilities to choose for this gamma p. So if we put gamma p equal to 0, and you immediately see what happens, because I just write it here. So you see if gamma p is equal to 0, our system matrix is just made up of the mass matrix, yeah, because the stiffness matrix K is scaled with 0. You call this a forward difference or forward Euler method, which is in general not really applicable. Why? It is the following case. I have to go back, perhaps, in order to show it to you. I just want to go back where we have computed the mass matrix. And perhaps you remember that the material parameter entering the mass matrix, yeah, here we have it, is, sorry, here we have it, is the electric conductivity gamma. Yeah, and mostly you always have also within your computational domain air. In air, for example, the conductivity is 0, and then you would have 0 entries on the diagonal, so you cannot solve your system. So in this case, for the quasi-static electromagnetic field computation, this is not a choice which makes really sense in practice. Perhaps you know that the most accurate scheme would be to use the Crank-Nicholson one, which means that this parameter gamma p is set equal to 0.5, and at last, full implicit, as we also call it, would be the backward difference or backward Euler scheme, where we take for our time integration parameter gamma p equal to 1. Okay, so let's summarize it. So the time integration parameter gamma p being larger than 1, we call such a time discretization scheme always an implicit scheme. And as you know, the system matrix then is a superposition of the mass matrix and the stiffness matrix. What you obtain is also called the absolute stable scheme. So you have no restrictions on the time step delta t if this integration parameter is larger or equal 0.5. So even for this case where it is larger than 0 but smaller than 0.5, we have some restrictions on the time step in order to get at the end a solution, and that you don't diverge when you compute a lot of time steps. The rule of thumb is the standard rule for all partial differential equations. In this sense, you have you look at your excitation. In our case, it's the current density, which could be any or will be any function of time. You compute the maximum frequency within your excitation and take about 20 time samples in this sense per smallest time period defined by the maximum frequency. And for this case, you get delta t. Okay, so this you should know. You should know your excitation, the right-hand side of your partial differential equation. For us, any current density given in a coil, for example, or any conductor. And in this sense, then we have this as a rule of thumb in order to get also an accurate time discretization, which you can use in practice. Okay. Now, just let's have a simple illustration here. We have such a coil here where a current is going in this direction. As you can see, I should switch on my pen. It is going in this direction. We explore a quarter symmetry, and in a first computation, we put here a DC current, and on the top we have an electric conductive plate. Well, if you do this, the result will be as follows. Since the copper we have here has a magnetic permeability which is more or less the same as air, you will have here a solution which you would also get when you do not consider here this electric conductive copper plate. However, what you have to be careful, it is the steady state case. So if you immediately switch on and you compute you do a time step, a transient analysis, then it is clearly a switching on of the current, and you would have here also some transient cases. But when you do clearly here a static analysis, because the coil current is a DC current, then clearly you will get this result. On the other hand, you clearly also know that the copper plate is like a shielding. So when you have here any time changing current within the coil, then perhaps you see, as done in this computation, you do not see really any magnetic fields here above the copper plate, which is clear because, as you know, we induce eddy currents in the copper plate, and the eddy currents will also generate a magnetic field, but this will be opposite to the original field being generated by the current in the coil. And that is, as you know, according to the rule of Lenz. And what you also nicely see here in post-processing is here the eddy currents in the copper plate, and clearly they are in opposite direction, and due to this effect, as you know, it is also very effective for DC currents, and you want to shield the magnetic field, this AC magnetic field, to use a copper plate in this sense. Okay, so these are the effects you should get